Hello students, so in this lecture we'll study about the cavity resonators and in particular we'll study the rectangular cavity. Rectangular waveguide we have already seen. It was hollow metallic tube which was used for guiding electromagnetic wave. This Z is equal to 0 plane and Z is equal to L plane was open in rectangular waveguide. However, if we enclose this Z is equal to 0 plane and Z is equal to L plane by a metallic plate, then it becomes a enclosed structure which is metallic. So if anyhow we allow the electromagnetic wave to enter into this metallic enclosure, it will be reflected back and forth through the walls of cavity. So after some time the resonance may occur. That's why they behave as resonators and they exhibit resonance behavior when excited by electromagnetic field. These are also called cavity resonators. And these types of cavity resonators are used at frequency above 3 GHz. Since the electromagnetic energy is confined within its structure, these cavities are used for storing electromagnetic wave. Or you can say the electromagnetic energy is confined within its structure or stored within its structure. The stored electromagnetic wave inside this cavity determines the capacitance and inductance of the waveguide, equivalent inductance and capacitance of the waveguide, and the power dissipated in the form of heat through the walls of cavity determines the equivalent resistance. Since we have all R, L and C, we can determine the resonant frequency. Okay, so the resonant frequency is the frequency which determines the resonance behavior of this cavity. A given resonator will have infinite number of resonant modes within it, and each mode correspond to definite this resonant frequency. Each mode will have different resonant frequency. These modes, since we have infinite number of modes within it, these modes are determined by solving Maxwell's equation and applying boundary conditions to appropriate configuration. When the frequency of impressed signal, let's say it is F, is equal to the resonant frequency of particular mode, then the standing wave pattern that would have appeared due to reflection through the walls have maximum amplitude, and the peak value of stored electric energy and the magnetic energy will become equal. This is the resonance condition. When the frequency of impressed signal is equal to the resonant frequency for particular mode, then the stored electric and magnetic energy will become equal, and the standing wave pattern that would have appeared because of reflection through the wall will have the maximum amplitude. Here in this figure we are seeing this rectangular cavity where we have placed a metallic enclosure at Z is equal to 0 and Z is equal to L also. This is a metallic rectangular waveguide which is shorted at Z is equal to 0 and Z is equal to L. This is illustrated in this figure where A is greater than B and less than L. This cavity, this particular cavity will be resonant at the frequency when L is multiple of lambda G by 2. resonant condition will occur when L will be multiple of lambda g by 2, where P could be anything 1, 2, 3 and so on, where lambda g is, you have already studied in rectangular waveguide, it is guide wavelength. Okay, so this is rectangular cavity which is shorted at z is equal to 0, z is equal to L, and it will be resonant when L is multiple of lambda g by 2. To verify this condition, let's see an example. So suppose we have shorted this rectangular waveguide at z is equal to L, means at z is equal to L it is shorted, and it is not shorted at z is equal to 0. Let's say z is equal to 0 is not shorted and z is equal to L is shorted by a metallic plate. Now at particular frequency, let's say z is equal to, at z is equal to 0, an electric field is sent which is 0 at z is equal to 0. This electric field which is allowed to enter into this cavity, this enclosed structure at z is equal to L, has 0 at z is equal to 0, and we have a metallic plate at z is equal to L. So what will happen at the conducting surface? Boundary condition says that the tangential component of electric fields will be 0, means Ex will be 0 and this Ey will also be 0 at z is equal to L. Let's see here what I am saying. Suppose this is the structure we have, let me draw it again. This is the structure. We have shorted at z is equal to L. This is z, this is x, y. It is shorted at z is equal to L, and the wave is allowed to enter through this point, z is equal to 0. Since it is a metal here, the electric field components, what components? Ex and Ey will be 0 here, because it is a metal boundary condition. Your conducting boundary condition says that tangential component of electric field will be 0. Since it is a metal, so the electric field will eventually be 0 at this particular point. And we already know that if the electric field is 0 at this particular point, so this length must be the multiple of wavelength, lambda, half wavelength, lambda g by 2. Then only this condition would be appropriate. Otherwise, what would happen? This allows wave to be 0 at this particular point, and if it is not, lambda g by 2 will have 0 here and it will eventually lead to 0 here. The standing wave pattern would not be appropriate. Okay, so in order to have appropriate standing wave pattern, having null occur at each lambda g by 2, we want null occur to each lambda g by 2. That's why we are making this length equal to multiple of lambda g by 2. So these are two particular cases. In this particular case, P is equal to 1, and in this case, P is equal to 2. So this length is lambda g by 2. We have two nulls at lambda g by 2. It is 0 here, the wave is 0 here, which is scientifically correct. Means nulls occur at each lambda g by 2. Here we have P is equal to 2. Means that this length is L is equal to lambda g, means here we'll have two nulls occurring within this particular length. Okay, if this is not lambda g by 2, it will eventually lead to 0 here. Okay, please understand what I am trying to say. It will become 0 here. This magnitude will be higher, this magnitude may be lower, or it will not be the appropriate standing wave pattern. Okay, so in order to have the appropriate standing wave pattern within this structure, this length is considered as multiple of lambda g by 2. And the mode, resonant mode, are designated as T, E, M, N, P. Why we have considered P here? Because it is different than the earlier considered nomenclature, which was used as T, E, M, N for rectangular waveguide. Now, M represent number of half waves of electric or magnetic field in x direction. N represent number of half waves of electric or magnetic field in y direction, and P represent number of standing wave patterns within in z direction. So this is the definition of M, N and P, which is written over here. M represents number of half-wave periodicity in x direction, N represents number of half-wave periodicity in y direction, or P represents number of half-wave periodicity in z direction, or number of standing wave pattern that would have been formed here in this structure because of reflection through the wall. Here P is equal to 1 and we have one standing wave pattern. P is equal to 2. Here in this structure we have P is equal to 2. So we have two patterns in Z direction which are standing wave pattern. Now here in this example, we assume that Z was open and Z is equal to L was closed. And we said at particular frequency we are allowing only those uh, waves which have null at z is equal to 0. So if we put a metal wall here also, this would not disturb the standing wave pattern, and it will appropriately follow the boundary conditions too, because we are allowing the signal which are null at z is equal to 0, and they will eventually become null at z is equal to L, because we have considered the length equals to multiple of lambda g by 2. So if we put a metal wall here, it will not disturb any standing wave pattern. Now see, this M, N and P will be, the value of it will be either 0 to infinite. So for TE mode, if we have considered TE, M and P mode, then M may be either M or N may be 0, like we studied in waveguide, and the P will not be 0. It will be for TEMN mode. For TEMN mode, M may be 0, 1, 2, 3 up to infinity. N may be 0, 1, 2, infinity. Both of them together cannot be 0. Like we studied that TE00 mode does not exist. Either M or N could be 0 at the same time, and P will not be 0 anytime, because we want standing wave to occur within it. So it will be 1, 2, 3 and so on. For TMMNP mode, TMMNP mode, M will be from 1, 2 and so on, N will be 1, 2 and so on, and P will also be from 1, 2 and so on. None of the component M and P will be 0 in TMMNP mode. Now see how these standing waves are formed here. Standing waves are formed when we have two oppositely directed traveling waves within the structure. How this oppositely directed traveling waves appear within this structure? We have sent a wave which is traveling in forward direction from z is equal to 0 direction. We are sending forward directed wave through z is equal to 0, and it is being reflected by the metallic plate at z is equal to 0. So we have a wave in this direction, a wave in this direction. They will interfere with each other and will have standing wave produced within this structure. So we can say that it is a z-directed TE or TM mode, right? Because we have already considered that it is a rectangular waveguide. It is a rectangular waveguide which is enclosed at z is equal to 0 and z is equal to L. So if it is enclosed at z is equal to 0 and z is equal to say, and standing waves are formed due to this metallic enclosure, we can say the waves that is appearing within this structure are called z directed TE or TM mode. Now one could argue that x is equal to 0, x equal to a is a metallic enclosure, y is equal to 0, y is equal to b is a metallic enclosure. So there may be waves, standing waves forming within this structure also. But earlier what we considered that this xy is called transverse plane in waveguide, and wave was propagating in positive z direction. That's why we have said here that it is z-directed TE or TM mode, or standing wave patterns are formed in z direction. If we would have considered that wave is propagating in x direction, then we'll keep the hollow structure at x equal to 0 and x equal to infinite. It will be a hollow structure, and other way around it would be a metallic hollow tube. Okay, so here we say that it is it earlier it was hollow in z direction, so we are saying it has z directed TE or TM mode. Now since we have considered that a is greater than b and a is less than L, which is the dimension along z direction. In TE, in a rectangular waveguide, the dominant mode, which in a rectangular waveguide was TE10 mode. Now here we'll have the mode which has lowest resonant frequency is TE101 mode. This mode is called dominant mode or the primary mode. The mode having lowest resonance frequency is called the dominant mode or the primary mode. This mode is TE101 mode. TE10, let's say what does it mean TE101? Number of half wave variation along x-axis is x. Number of half wave variations along y-axis is 0. Number of half wave variations along z direction is 1, which is this case. P is equal to 1, the first case that we saw. In this case, we have one standing wave pattern along z direction. TE102 mode means we have number of half wave variations along x direction is 1, number of half wave variation along y direction is 0, number of half wave variations along z direction is 2, like in this case. In this case, TE10, there are two half wave variations in z direction in TE102 mode. Now let's derive the equation for resonant frequency. Now let's see the guide wavelength in a rectangular waveguide was defined as lambda g is equal to lambda over under root 1 minus fc by f whole square. In terms of lambda, it could be written as, since lambda is equal to c by f, we could write this equation in terms of lambda only, like this: 1 minus lambda over lambda c whole square. Let's give it equation number 1. We defined lambda g through the value of L in our earlier discussion, that the length L or along the z direction for the rectangular cavity is multiple of lambda g by 2. We for P varying from 1, 2, 3 and so on. So we'll put this value, this equation number 2 into this equation number 1, and since this whole discussion is for rectangular cavity where we are defining the resonant mode, so we'll make this lambda equal to lambda r, representing the resonant frequency or resonant wavelength, and we'll put the value of lambda g from 2 to 1. We'll get lambda g is equal to 2L by P is equal to lambda r divided by under root 1 minus lambda r by lambda c whole square, where lambda r is resonant wavelength. So, what is lambda c? Lambda c is cutoff wavelength. This cutoff wavelength will be decided on the basis of waveguide modes. Okay, so what was the cutoff frequency definition in rectangular waveguide? Fc is equal to c by 2 under root m by a whole square plus n by b whole square. Okay, means lambda c will be equal to this lambda c is equal to c by fc. So we could write lambda c definition as 1 by lambda c square is equal to m by 2a square plus n by 2b square. Now move on to this equation, equation number 3. So we are squaring this equation number 3. This equation will become 2L by P whole square is equal to lambda r square divided by 1 minus lambda r by lambda c whole square. And this equation will become 2L by P whole square is equal to 1 by, we are dividing the equation by lambda r. This will become 1 by lambda r square minus 1 by lambda c square. So it will become 1 by lambda r square is equal to 1 by lambda c square plus p by 2l whole square. We'll put the value of 1 by lambda c square from this equation, equation number 4. This value of lambda c square will be put from 4 to this equation 5. We'll have 1 by lambda r square is equal to m by 2a square plus n by 2b square plus p by 2l square. So this is the equation for resonant wavelength. By using the definition of lambda r and fr, lambda is equal to c by f, we'll define the equation for resonant frequency, which will be P by under root mu r epsilon r under root m by 2a square plus n by 2b square plus p by 2l square. So this is the definition for sorry, this is resonant frequency. Okay. So the dominant mode or the primary mode is the mode which has this lowest resonant frequency, and for rectangular cavity the dominant mode or the primary mode is TE101 mode.